So let's get started on chapter 11. Good place to start is in the beginning. So we'll look at the first problem here, chapter 11.1. And this chapter is about applying exponential models to the real world. So now here in this problem, for instance, they're saying that in 1968, the minimum wage was $1.60 an hour, which I think these numbers are true. In 1976, it was $2.30 an hour, and let's assume it's growing exponentially, which it might not be, but whatever, we'll just assume it is and see what kind of formulas we get. Okay, now they want us to see what happened in 1960, so we'll call 1960 t equals 0. We're not going to worry about before 1960. So if 1960 is t equals 0, then 1968 is t equal 8, and 1976 is t equals 16. It's a lot easier dealing with time 0 to 18 than dealing with these big, huge numbers. We could use 1960 and everything, but it's way better to just call that the earliest time we care about 0, and then everything after that. It just makes it so much simpler. Okay, so that's one thing we'll do. So part A then says, what is the wage as a function of time if we assume an exponential model? And exponential models are the amount at time 0, or the wage in this case. I could put a W there for wage, but this is the way that we wrote it last chapter, so whatever. Whatever it was at 0 times some base to the t, to the time. This base tells you how big it grows. If that number is big, then it's going to be growing really fast. And if it's small, it's going to be growing slowly. It's got to be bigger than 1 to grow. Right? We got a number bigger than 1 multiplied by itself many times, so we'll give it a number bigger than 1. If the base is less than 1, it's going to shrink. 0.9 times 0.9 times 0.9. You're always taking a fraction of a fraction. It'll shrink. So how big this base is tells you how fast this thing will grow, how fast the minimum wage grows here. Okay, so we have 2 data points. We know 1968, 1976, and we have 2 things we don't know. We don't know A0 and we don't know B. So they have to give us 2 things to find 2 things. So now we're going to solve 2 equations and 2 unknowns. So let's start with 1968. The wage was $1.60, and that's equal to A0, B, and the time was 8, because we're going to use this, not 1968, right? So this time equals 8 years after 1960, so B to the 8. And then in 1976, it was $2.30, which is A0, B, and that was year 16. Okay, so those are our 2 equations. We need to find out from these 2 equations what B is and what A0 is. There's different ways to do this. I find the easiest way is to get rid of the A0, right, because it's just sitting there. So let's divide the 2 equations, okay? And since I like dividing big numbers by small numbers, we'll take this one, 230, we'll just divide both sides. So we have 230 over 160 on that side, and this divided by that, and over here we have this one, A0b to the 16th divided by A0b to the 8th. Again, just dividing each side. Now, what's really nice is the A0s cancel. That's why we did that. And b to the 16th divided by b to the 8th, we're just taking away 8 of the b's, and that's equal to b to the 8th. So now we just got to get a calculator and figure out what 230 divided by 216 is, 160 is. So 2.3 divided by 1.6, I get 1.4375. So 1.4375 is equal to b to the 8th. And again, you always just subtract 16 minus 8. 8 of those cancel out 8 of those. 16 minus 8 is 8. So we want b now. We know what b to the 8th is, so we got to take the 8th root of each side. So in other words, we raise this side to the 1/8 power, raise this side to the 1/8 power. Whenever you have a power to power, you multiply. 1/8 times 8 is 1. That's why we're doing this. So b then on this side is equal to this to the 1/8. So this is where you got to know how to use a calculator. So I'm going to raise 1.4375 to the 1/8 power. Mine, I go y to the x, 1 divided by 8 I get 1.046. 1.0, actually 1.0464, then it's 0, so I might as well keep all those. So B is equal to 1.0464. Now we know what the base is, and it makes sense. It's bigger than 1. You better get bigger than 1. And it's not a very big number, so it's not growing really fast. It's not doubling. If base was 2, it would double every year. It's not doubling every year, right? It's just got a little bit. It took, in 8 years, it only went up 70 cents. It didn't even come close to doubling. Doubling would have been 3.20. So, maybe it looks right. It doesn't mean it's right, but it looks like it could be right at least. Okay. So now that we know what B is, we need to figure out what A0 is. So we can use either equation. Let's use the first one because it's first. So we know we'll use this one. So 160 is A0. We know what B is now. So that times 1.0464 to the 8th. All right, just using this equation. We don't know A0. We know B is that to the 8th. We want to solve for A0. So A0 is 1.6 divided by 1.0464 to the 8th power. So now I got to do that to the 8th power. So again, I know how to use a calculator. 1.0464 y to the x 8 is equal to that, 1 over that, times 1.6. And I get 1.1131. So let's just keep it up to the 3. So that's 1.113. Now we know everything we need to know. Our wage as a function of time is A0, 1.113, times this number. I'm going to put it in parentheses, make it clear, 1.0464 to the 8th. That's our base. That's the number. So this number in front, when at time, sorry, this is to the t. For any time, not just the 8th. This is to the t power, right? To the t power. So that formula is good for any time, after, assuming t0 is 1960, right? So if we plug in t equals 0, anything to the 0 power is 1. So in 1960, the minimum wage, according to this model, who knows if it's right, would have been $1.11.3 cents or something, whatever that is, $1.11 per hour. Okay, then I think that's part B, saying what it is in 1960, right? It's just the number in front. That's what that number means. The time at time 0 to 1960. Okay, if the minimum wage was $5.15 in 1996, is this above, below, or equal to what the model predicts? Okay, so in 1996. Let's see if it was 5.15. So part B was, again, this. You just read off that number. That's what the minimum wage was in 1960. Part C, what is it in 1996? Let's see. 1996 would be year, what? 1996 minus 1960, 36 years? Yeah, 36. So that'd be year 36. We plug in 36 here. So the wage in 1996, which is year 36, is 1.113 times 1.0464 to the 36th power. So again, this is just a calculator problem to test our model here. Let's see if we get, let's see what we get, see if we get what they said. So 1.0464 36 times 1.113. Okay, I got 5.6965. That's about 5.70. Rounding off to the nearest penny, 570. So this model says in 1996 that you would be getting $5.70 an hour for the minimum wage. And it really was, they say, and I think this is real numbers, they said it was really 5.15. So obviously our model is a little bit too big. We get a little bit too much. So this model is not perfect, at least not for that, yeah. Okay, so that's the idea with exponential models. You use this formula, you have to know 2 data points. You plug those in, the times. Sometimes they give you how much it starts off with. If they give you that, that's easy, right? If they say it starts off with 30, then you know A0. That makes it a lot easier. Here they didn't tell us what it starts off with. We don't know what it was in 1960. We just have 2 later data points. That makes it harder. Then we got to do all this work and solve for A0 and B. But if they give us A0 or something, that makes it a lot easier. And let's see, what else was I going to say about this? And yes, I guess that's about it. Remember this formula, that whatever it is you're looking for is something b, a base to the time. It could be x, whatever, if it's not correct time. So, okay, good. Hope that makes sense. Number 2 is very similar. They say also make a linear model, compare it to the exponential model. Exponential models are always going to end up growing faster, and see maybe which one, what they predict for later on. So, pretty cool. Okay, this stuff is really fun. I think it's really cool to do exponential modeling. Good skill to have. And, goodbye.